with a definition here. So this is basically the definition which gives us a characterization of connected sets. A set E is separated by open sets U and V if the following three conditions hold. First condition is that E is covered by the union of U and V. So E is a subset of U union V. Second condition is that E intersect U intersect E intersect V is empty. So this is just to say that the pieces of E that are covered by U and the pieces of E that are covered by the open set V are disjoint. Okay, so that's the intuitive notion of E being separated by the two open sets. And the third condition is just kind of, more trivial, but we need to include it, which is that E intersect U should not be empty, and E intersect V should not be empty. Okay, so to draw a picture here, I have some set E, which might be a little weird, and here's E, and then it's going to be separated if I can draw two open sets. Here's U and V, such that the following three things hold. Okay, so basically a set is considered connected if it cannot be separated by any two open sets. Okay, so let's get to that. Okay, so set is connected by any two open sets. Great. Okay. So let's get into the statement that we're trying to prove here. Okay, so my claim is that a set E in RD is connected. Show that E closure is connected. All right, wonderful. So this is our claim. Let's get into the proof. So to prove this, I want to use this definition of set being separable by two open sets. And so the clearest way to get into that definition is by a proof by contradiction, right? If I suppose first that E is connected and E closure is disconnected, I can use the definition of disconnected, which is that I can find two open sets that separate E closure. And then I can try to derive a contradiction from there. Okay, so that's going to be basically our proof strategy. Okay. Okay. So let E be connected. Suppose, for sake of contradiction, that E closure is disconnected. then we're going to be able to separate it by two open sets, U and V open sets, such that U and V separate E closure. So again, E closure is a subset of U intersect V, U union V, my bad. E closure intersect U, intersect with E closure, intersect V is empty, E closure intersect U is non-empty, and E closure intersect V is non-empty. Okay, so U and V are going to separate E closure. And now we want to ask ourselves, how do I derive the contradiction that I want, that ultimately U and V must separate E? Okay, so since E is a subset of E closure, okay, this first condition is going to hold for E as well, and the second condition will also hold for E. So the condition that must fail if E is connected, and therefore cannot be separated by U and V, is this third condition is going to fail. Okay, so since E is connected, actually let me put it this way: U and V will also separate E, since of course E is a subset of E closure. U and V will also separate E unless the third condition fails. So the third condition failing means that E intersect U will be empty, or E intersect V will be empty, okay? So without loss of generality, let's assume that E intersect U is empty. When I say without loss of generality, I just mean one of these is going to hold true, and in either case the proof will be identical, okay? So without loss of generality, assume that E intersect U is empty, okay? All right, so we're pretty much there. Well, there's some more work left to be done, okay? So since E intersect U is empty, but E closure intersect U is non-empty, we need to use the definition of the closure, which is the sequential definition, which means we take E and we union it with all of its limit points, okay? And we use the sequential definition of the closure to gain a contradiction here, okay? So let me just erase this. Okay, so what do we have now? We have that for E to be connected, E intersect U is empty, but E closure intersect U, remember, since U and V separate E closure, this is not empty, okay? Now the sequential, a closure of a set is the smallest closed set which contains that set, but there's a sequential definition of the closure, okay, which, if you recall, is the set of all limit points of sequences xn in E. Convergent sequences, we could say. Okay, so I take E, I take all of its points, and then I look at all of its limit points, and the closure is going to contain not only the set E itself, but the limit point of every sequence belonging to E. So intuitively, like suppose this was E and maybe I had some crazy stuff happening in the boundary here, maybe this part of the boundary is open or something like that, then if I take any sequence, I can approach this boundary, and if I include the limit point of that sequence, I'm essentially closing the set off. Okay, so the boundary of a set is going to be the set of limit points of sequences that lie in the set and also a sequence in the complement of a set. Okay, so if we include limit points of sequences in the set, we're going to gain the boundary. We're going to gain access to the full boundary of the set, and so therefore we're going to get the set union its boundary. Okay, so I won't prove this right now. It's a useful exercise to show that this is actually true. But okay, so we have this in hand. Now, what this means is that since E closure intersect U is non-empty, okay, there exists a point X in E closure such that, or I guess we could say X is, X and E closure intersect U, okay? So this point is in E closure, okay? So therefore it's going to be the limit point of a sequence in E, okay? So therefore, there exists a sequence in E, xn, we'll say, which converges to X. All right, so we're almost done. The sequence in E is also in U complement because E intersect U is empty. That's the key step. Since E intersect U is empty, this sequence xn is in E intersect U complement. Okay? In other words, xn is going to be in U complement for all n. But U complement is a closed set because U is open. So this sequence xn, which converges to a limit point x, the sequence lies in a closed set, so its limit point needs to stay in the closed set, U complement. So this is a contradiction, okay? So let's write that out. Okay, so we have a sequence, xn lies in E intersect U complement, which is a subset of U complement. Since U complement is closed, every convergent sequence converges to a limit point in U complement because it's closed. So X must lie in U complement. That's a contradiction. Again, the reason this sequence lies in E intersect U complement is because E intersect U is empty. So xn lies in E, which is equal to E intersect U complement, right? Because E intersect U is empty. And then since this sequence lies in a closed set, its limit point is convergent, its limit point has to stay in the closed set, its limit point has to be in U complement. So this is a contradiction, okay? So the key to this proof is recognizing, using the definition of separability, and then recognizing that the fact that these two sets which separate E closure are open means that if we take a sequence in E, okay, its limit point is going to belong to E closure, and if that sequence in E lies in one of those two separated sets, it has to stay, it can't jump to the other one, right? Okay, so that's it for today. Thanks for listening.